Okay, good afternoon. First up, today I want to just cover the quiz 7 solutions. That was the diode analysis using constant voltage drop model. And then, that way students have an opportunity to ask questions if you wish to. All right, so let's see, quiz 7. We had a circuit made up of 3 diodes. Our V1 voltage source was for 6 volts. And V in varied between plus and minus 10 volts. And we're asked to find V out is measured between the terminals on the right. Okay. And we are using CVD model. So CVD model for analysis. And the diode voltage drop VD is 0.7 volts. If it's not given, you can assume any value. Well, any value within reason. So 0.6 or 0.7 is fine if it's not given. All right, so what's the first thing we do when you have a source connected to a diode? Let's take a look at what the potential is at either terminals of the diode. So in this case, the cathode of the diode is held at E1, D1, yep, minus 6 volts. So for D1, cathode is held at minus 6 volts. So what would it take to turn this diode off? If the cathode is always at a negative potential, that means if the anode is 0, anode is higher than the cathode, so diode is on, right? So for all values between 0 and plus 10, diode D1 is always on. What would it take for that anode or for the diode to turn off? Right? Anode must go lower than the cathode. Does everyone agree? What voltage we need? We need the anode to go below 6 volts minus the diode voltage drop. So I would say for V in between 0 to plus 10, D1 is always on. Or V in below 0 all the way up to minus 5.3. D1 is on. In order for it to turn off, V in must be lower than 5.3. Let's put it this way. Lower than 5.3, D1 is off. Okay, that's one branch. I'll pause for a few seconds. Let me know if you have any questions about this branch. Right now, we are only focused on this branch, right? That's where the source is connected. So my first focus is always on that branch. Yes. Yes, negative 5.3. Thank you. Negative 5.3. Okay. Now, if it's on, and you can think of your questions, I'm just going to draw this out. Hence, sorry. plus minus 5.3 volts between the two. So this is the on state. Okay. All right, let me know if you have any questions. Does this make sense so far? Right? All right, so we established now D1 is on for pretty much all for the entire range of input, except when Vin goes below minus 5.3. When it goes below minus 5.3, diode turns off. That branch is completely disconnected from the circuit, right? So diode is off. That branch is disconnected. Okay. So we found the range of operation for that diode. We'll leave it to the side. What about diodes D2 and D3? What is required to turn them on? So only two diodes, right? And CVD model, so 0.7 plus 0.7. We need 1.4 volts. But because they're flipped with reference to our V in supply, we need the voltage to go below 1.4. So for the second branch, for D2 plus D3, for V in greater than minus 1.4 volts, diodes D2 and D3 are off. Negative simply means the voltage supply V in is flipped. That's all it means, right? You're flipping. That's all it means. So positive terminal is at the bottom. And for V in less than 1.4, D2 and D3 are on. If they're on, they look like this. You have minus and plus, minus and plus. So there is a constant voltage drop of 1.4 volts between our output terminals. So what is our V out? That is our V out. Remember the terms, constant voltage. Once the diodes turn on, they are providing us a constant voltage. Okay, this is a model. CVD model means we are modeling our diode as a constant voltage source. So they're in the name itself. So the current through the diodes can increase, but the voltage will remain constant. So V out is minus 1.4 volts. when the diodes are on. Right, let's take a pause. Let me know if you have any questions. Yes. Sure. More practice and advanced. Okay. Question being asked is where more practice problems. I'll go ahead and post it to Canvas. I'll post some to Canvas. Okay. This essentially is the same. This essentially is the same circuit we did in class, except the voltage source is flipped. Yes. Mm-hmm. Yes. Yes, we're going to talk about that just in the next third. So we are focused on the two branches first. Now we're going to combine the two branches together and see what the actual output is going to be. So we're heading to that question. Yes. You had a question here? Same thing. Okay. All right. I just want to make sure both branches are understood before we move on. Okay. So now the key word here, as I said, CVD model, right? Constant voltage drop model. Diode is a nonlinear device. We've already looked at that. We've established that. The current for the diode increases, right? So CVD model, if you recall from those first few slides about CVD topic, the VI or IV characteristics of a diode is a vertical line at 0.7 volts. Does everyone remember that? So the vertical line indicates that the current increases, but the voltage remains constant, right? So the input voltage can keep on increasing. If the input voltage keeps on increasing, that means it's supplying more current. So the current through the diodes keep on increasing, but it'll hold the voltage constant. So when you combine these two branches together, which is between, as was pointed out earlier, between 5.3 and 1.4, all of them are on. What happens then? Well, when you combine those diagrams together, this is what happens. So 0.7, 6 volts, and then we have this. Our V out will still be minus 1.4 volts because the excess current is going in this loop and this loop. But the output voltage will be held constant. So the 6-volt supply and the and V in combined, the current through that resistor will increase. Current through the diodes will increase, but the voltage across the diodes will remain constant. Yes. With ideal wires. Uh-huh. No, V in is 0 volts. If V in was 0 volts, okay. Mm-hmm. It'll go through the resistor. Mm-hmm. So yeah, KVL will be violated. That's essentially what you're saying. That's a very good question. Oh, if you apply KVL here, I'll have to look at that, but I ran this simulation, and the simulations confirmed with my calculations that V out should be minus 1.4. So I'm not really sure where. When you say ideal wire, you're talking about these, right? That there is no voltage drop across here. Okay. There's no resistance between the diode, yes. Actually, I'm stumped. I don't have an actual answer to your question right now. So let me think on this a bit, and then hopefully I'll have a better answer by Friday. Hopefully. It worked in Spice. Sorry. Well, I ran the simulation in Spice and it worked. But Spice does not use CVD models. It uses it uses real diode models. So the voltage does come out to be constant across both the branches, but it comes out to be about 3.9 to 4 volts. So in LT Spice, when I simulated this with real diodes with 0.7 volt silicon diode, 0.7 volt drop, but it's not a CVD model, but it works. It comes out. So maybe CVD model might not work for this one. And if that's the case, then there will not be any penalty for students as long as the work is done. More across the 1.4. Yeah. Yeah. Anyway, so as I said, simulations do work with the real diodes, but with CVD model, perhaps this gets KVL gets violated, so it might not work. It does. Yes, it does. Yes, real diodes. Yes, it does. That's where I actually got the idea to do this, but I didn't think about applying KVL there. Yes.
So somehow, by some means, I got the same answer. The only reason why, because I assumed that because KVL was violated, the leftmost power source of 5.7 or negative 5.3 volts was short circuiting all the current to itself, and the other part went through.
It
The only reason.
It does, because a voltage source is essentially a short circuit. So the current does flow through here, but that still doesn't allow us to do this loop. So anyway, that was my procedure for the solution, but I'll take a look at it more in depth and see if yeah. This one, Keone, did you have a question? Which one? This one? That's what we were discussing actually. Most of the voltage drop should be across the resistor. And then again, in real life diodes, it'll be dropped across the diode resistance. So there'll be a slight voltage increase across the diodes, but in CVD model, there is no increase. So the real life diode model, it will work. So if you simulate this in LT Spice, it will work. But if you change the series resistance to 0, perhaps it might not. So that's what I'm going to try and see if that works or not. Your question was, the question, actually it's 1:30. How did we arrive at 1.4? Okay, all right, okay. All right, so as I said, this was my methodology. The one thing that I'm going to try with the simulation is instead of having series resistance in the diode model in LTSpice, I'm going to run with like 0 or like 1 milliohm resistance and simulate it and see if it matches with this assumption. See if we can figure out if there's any extra voltage drop across the resistor. And then if it doesn't, then we'll discuss it on Friday. Okay, comparators. So switches and elementary logic gates, and then comparators. We looked at pull-up resistors and pull-down resistors. One of the reasons they are not very widely used is because of static power consumption. Static power consumption refers to the energy that is consumed when the system or the circuit is not used or not in use. Okay. So in pull-up or pull-down resistors, you have connections made to VCC, and then you have your out, right? And then also in pull-down resistors, when the circuit is connected, again, you have a resistor in the pathway. And so even when the circuit is not being used, or if it's in a fixed position, there's always current flowing through the resistor. And because there is current flowing through the resistor, your it increases the power consumption. So static power consumption is not zero. So pull-up and pull-down resistors are not favored while creating these kind of logic gates. What is favored is using CMOS technology. CMOS stands for complementary metal oxide semiconductor transistors, and that is basically the transistors that we use in all modern day chips. So all of our microchips that we use today, going back the last few decades, they all use MOSFETs. MOSFETs, again, stands for metal oxide semiconductor field effect transistors. And that is something we'll look at in 315. Okay. Let's see. Oh yeah, in that CMOS transistors, there's a pair of them connected in series. And then when one is on, the other one's off. When one is off, the other one is on, and vice versa. And so the resistance for these kind of devices is typically very high. So it's total cutoff. And because it's total cutoff, there is little to no power consumption in an idle off state, unlike the resistors. Okay. So that's why resistors do not use, that's why modern logic gates do not use pull up or pull down resistors. Okay. Have you used comparators in the lab? Right? You already done that. So you observe the rectangular waveforms, output waveforms. Okay, great. So this is the actual symbol for a comparator. Looks very similar to an op-amp. More often than not, this symbol right here that's showing you the transition between 0 and I'm just gonna label plus 5 volts or any high level. Okay, so the output of a comparator is always a straight line, either 0 or plus 5, assuming we are talking about 5-volt digital circuits. Okay, and there are two terminals. One is labeled as positive, the other one's labeled as negative. If the negative terminal is higher than the positive, then the output goes to 0. If the positive terminal is higher than the negative, output goes high. That's it. That's the essential function of a comparator. That's all it does. What are some real life applications you think of these kind of comparators? Sure, yeah, that is true. Phone X, whether it's charging or not, that's a very good one. Yes. Anyone else? How about thermostats? Heater control. We set our thermostats, or let's say like oven temperature or any other kind of temperature sensing system, to a fixed temperature setting. When the ambient temperature rises above or goes below your setting, it sends a signal. That electrical signal is fed into a comparator. One end, of course, of the comparator is connected to the setting for the ambient temperature. The other one is connected to our manual setting. And then depending on whether you choose heating or cooling, if it goes above or below the setting, that HVAC system would turn on or off. Okay. So if it's an oven, you want to heat it to like 350 degrees C, 350 degrees Fahrenheit. You set on the front panel, you set 350. That means internally on the digital circuit, you're setting one terminal of the comparator at 350. It heats up because the signal tells it, send the power to the electrical coil. Electrical coil heats up, crosses 350. Now the comparator is already at 350 and your own temperature is rising, reaches 350. It sends a signal, shuts it off. Does that make sense? Right? So any kind of heating or cooling system, digital comparator. Other is a turnstile, which is counting. So it compares the standard level with the movement of the turnstile. And so every time the turnstile moves, it's going to send a signal. It either raises or lowers the measured signal with the setting. And then that tells it, okay, go count. And so it implements a counter and it starts counting. Okay. So comparator has a wide range of applications in everyday life. Sometimes it's obvious at the consumer end, sometimes not so obvious. Okay, just some glossary. Power terminals are labeled as either VCC or VDD. Positive terminals or positive power rail is typically connected to VCC and VDD. The C and C comes from collector terminal of a transistor. The D comes from the drain collector of an FET, drain terminal of an FET. Logic circuits were implemented something known as transistor logic or MOSFET logic. And so these names go back to the terminals of those devices. The E and the S stands for emitter and source, which is typically connected to ground or the negative end of the power supply, hence VEE or VSS. Okay. And again, this is all something we will look at in 315. By the way, has registration begun for all of you? Not yet. Some of you. Okay. Okay. 215, I think there should be plenty of spaces for everyone. They design it that way. There should be 2 sections of 215. I'm not teaching 215, but I am teaching 315. So you won't get rid of me that easily. And I'm teaching both lectures as well as all 3 labs. So far, at least that's what they have scheduled me for. But you'll see me again in spring. All right. Open collector voltage comparator. You have a circuit that makes decisions, and that circuit's output is fed into a semiconductor device like a transistor This transistor could be a BJT or an FET. The collector terminal, the open collector, actually comes from the BJT configuration because the BJT terminals are collector, emitter, and base. FET terminals are drain, source, and the gate. Okay, so let's say you have this kind of semiconductor device like a BJT or an FET. It's pulled up to VCC. We're using a pull-up resistor at the output. When the switch is off, meaning it's disconnected, output is directly connected to VCC. When the switch is on, it's connected to the negative and VEE or ground. Okay. This electronic decision circuit, again, comparator circuit, plus and minus, meaning positive terminal, negative terminal. If positive was higher than the negative, it activates and output is 1. So let me write, oh, it's actually, just point this out here. Okay. V in positive greater than V in negative. Positive terminal is higher than the negative terminal, output goes high. And when negative terminal is higher than the positive, output goes low. That low could be either 0 volts or it could be some negative value. Okay, so similar to op amps, comparators can also have dual power supplies. Okay, not always necessary, but on the lab benches and installed equipment, you would be able to find dual power supply rails. One thing on the previous slide that I didn't mention was that op amps and comparators look to be very similar, right? So one of the things on the slide was that transition symbol is not always presented. In fact, actually, just reflecting back, I can't remember the last time I saw a comparator have the transition symbol. All textbooks and most images that we encounter, the transition symbol is omitted. So it's simply a triangle like an op amp, and it's just left to the understanding of the reader that this is a comparator. But there are two very different devices, right? Op amps can be used as comparators, but comparators cannot be used as op amps. So in a way, I like to explain it that comparators are a subset of op amps. That's not how everyone describes it, but I like to describe it that way because op amps can be used as comparators, but comparators cannot be used as op amps. Okay. All right. Now, using the thermostat example, we have, if you ever operated a thermostat, here we have an analog one, which doesn't even work in this room. But there are digital ones where the temperature can be set for every degree, right? You can increase it from in steps of 1 degree each, right? But there are other ones where the temperature can be changed down to 1/10 of a degree, right? With temperature sensitive applications. And there are even more specialized ones like scientific applications, engineering applications, where it could be even finer steps. So the thing here is that the finer the steps, the smaller the voltage difference between levels. Okay, so comparators are actually designed to sense even small changes in the voltage, going all the way down to millivolt range. Okay, so real life application. Is the smaller the step, the more sensitive the comparator needs to be, right? All right, any questions so far? Okay. All right, then there is a push-pull voltage comparator. Take a few seconds, let it sink in. What difference do you see from this one to the previous one? I'll bring it up again. Here you have two switches, and here you have a resistor. So what is the difference between the two? Is something that I just spoke about at the top of the talk. When you have a resistor in the circuit, absolutely static power consumption, right? So even when the circuit is not operating, we are not doing anything with the circuit, the output is connected to VCC and current is being drawn, right? Current is being drawn. So if we replace that with a complementary switch, then we get rid of that power consumption. It seems like a small thing because this power consumption is probably like, less than milliwatts. But consider the fact that even if it's microwatts, right, 10 raised to minus 6, you have billions of these transistors in a microchip, right? Billions is 10 raised to 9. So even if one transistor has 1 microwatt of power dissipation, you multiply that by a billion, now it's 1,000 watts, right? That's why we have these massive heat sinks on desktop machines, because the chip has billions and billions of these transistors, each one of them probably nanowatts or less, but the combined effect is tens of watts. Okay, so we replace that resistor with a complementary switch. The reason it's called complementary, well, one of the reasons it's called complementary is the fabrication differences. There's NMOS and PMOS transistors, again, 315. But for now, just suffice to know that if there's a bubble on the switch right here, it simply means it's negatively, it's implemented using negative activation. So a bubble on the input like this means negative activation, which is opposite of this one. This is positive. So switch SW1, positive activation, SW2 is negative activation. So they both are never on at the same time. It's impossible. Okay. If one is active, then two is off. If two is on, then one is off. Hence complementary. So if they're both never on at the same time, you have your output coming from this circuit, goes into both of these switches at the same time. But based on the signal, only one of them is going to be on at a time, right? So both switches cannot have the same state. Okay, they both cannot have the same state at the same time. When the positive terminal of the input is higher, then the output goes high. If the output goes high, wait, why is this should be the other way around? V out is equal to VCC. I think these two would be switched. Minus S1. These two should be switched. When positive terminal or positive input is higher than negative input, the output goes high, meaning this output right here. And if that output goes high, then S1 is activated and our output goes to 0. If V in negative is higher than V in positive, then output at the decision circuit goes low. And if that's the case, then output is connected to 1. Okay, so this, sorry, go ahead. Uh-huh. Yes, yeah. All they're doing is they're connecting it to VCC plus VCC and minus VEE. That's all it's doing. And the name push-pull comes from the fact that we're using this complementary connection of switches. Okay. Sorry. Oh, I'm just using that as a notation, high or low. So one would be VCC, and the other one would be VEE. So when it's 0, switch 2 closes. Let me write it here. Let's label this as V out at the EDC. Okay, voltage at the output of the EDC. So if V in plus is higher than V in minus, so this is V in plus greater than V in minus, output here is going to be 1 on VCC. If VEDC is 1, then SW2 is off and SW1 is on. If SW1 is on, you're out. What is out? What is the out? This is on, so my output is connected to VEE. Okay. And similarly, if V in plus is less than V in minus, then VEDC is 0 or VEE, meaning switch 1 is off and switch 2 is on. And if switch 2 is on, then my out is now VCC. Okay. Yes. Yeah. Yeah. Yes. No. So the question being asked is the circuit functions a little differently or the application is any different? Not really. Application is still the same. And even the operation here can simply be flipped by saying the switch 1 is at the top and switch 2 is at the bottom. And we'd have, and then this would be true. Okay. So if switch 1 was at the top and switch 2 was at the bottom, then whatever is typed in here in the slide would be true. All right, so this is a demo. There's two demos. Well, demo in the sense there's SPICE simulations. There's this one with a sine wave, and then there's this one with a triangular wave. Okay. In both cases, we are simply looking at the output of the comparator. Which ones did you do in the lab? Did you apply both sine wave and triangular? Or just triangular waveform? Okay. And did you all do SPICE simulations for that? Okay. Well, anytime in the lecture slides, yeah, the SPICE simulation is a good exercise for students to actually take and simulate themselves. All right, so you have this comparator, LT1716, you're applying 5 volts, plus minus 5 volts power supply to the power rails. And then in this example, we are fixing the positive terminal to ground. Positive terminal is fixed to ground, meaning it's at 0 volts. And you're applying a sine wave of 100 millivolts, 200 millivolts peak to peak. And then we're observing the output of the comparator. So the quick extension, not extension, but this is time. Time is in milliseconds. If you look at the output waveform, what do we see? Sine wave here is positive, and this is negative. V in plus is always held at 0 volts. That means anytime the negative input is above 0 volts, the output of the comparator should go 0, which is what we see here. 0. And then when the sine wave input goes below 0, meaning the negative terminal is below 0, now the positive terminal 0 is higher. If the positive terminal is higher, output of the comparator goes high. So we obtain a rectangular waveform. Okay. This, by the way, is a square waveform. Okay. The square waveform, because the duty cycle of this output is 50%. Exactly 50%. On is 50%, off is 50%. So this, we can say, is rectangular output. Or actually a square waveform, because it's a 50% duty cycle. Okay. And then that was a sine wave explanation. Here is the triangular wave. Again, this is something that you've already done. So setting up a pulse waveform to go from 0 to 10, but taking 0.5 milliseconds to do so. So 0.5 milliseconds on, 0.5 milliseconds off, total time period of 1 millisecond, which we can see here goes from 0 and ends at 1 millisecond right here. Okay. So positive half cycle is here. Negative half cycle is here. And now we are fixing the negative terminal of the comparator at plus 5 volts. So in order for the output to go high, then the positive terminal of the comparator, meaning V3, must go above 5 volts, which happens right here. And so when it goes above 5, my output goes high. For other instances, it goes low. Okay, so this is high and this would be low. All right. So we had to rush through a few things, but review the slides and the lecture video, and then prepare your questions, and then bring it to class on Friday. Okay. Also, please review the last two slides on here. This is more about sustainability and the effects, the real world effects of what happens with our electronics. Okay. So, yeah, please review those last two slides. Okay. And then we'll answer your questions and have a short discussion at the beginning of class on Friday. Also, the simulations in LT-SPICE, I would strongly recommend that students do run the simulations themselves. Okay. All right. Class here today. We'll see you all on Friday.